Hi everyone. Welcome to ECOWIN's Accelerate webinar on climate change and the seabed. Thank you for joining us today. So this is an ECOWIN program webinar. My name is Kimberly Lloyd. I'm one of the ECOWIN champions, a senior consultant at Howell Marine Consulting, and I'm going to introduce the webinar today. Okay, we're a minute in, so let's get going. So for those of you that don't know, the ECOWIND programme began in 2022 with the aim of delivering a robust evidence base to support the UK's ambitions around offshore wind. Mario, if I could just ask you to let everyone in for me. So we have 4 projects under ECOWIND. We have the ECOWIND project that's investigating what the cumulative impacts of offshore wind on seabed populations and the wider ecosystem to be able to support strategic compensation and net gain measures. Sorry, I am overcoming a cold, so I'm a bit croaky. We've got the Pelagio project, which is undertaking a physics to ecosystem level assessment of the impacts of offshore wind, with a focus on what happens when there is a change in mixing due to energy extraction. The Bowie project is taking a big data approach to understanding cumulative effects of multiple pressures on the benthic environment and the consequences of delivery of ecosystem services to society. And today's project is the Accelerate project. So they're looking at the wider ecological implications of changes to seabed sediments and ecosystem service delivery around wind farms. The focus of the webinar today is about climate change effects on the seabed. We all know we're facing twin crises of climate change and biodiversity loss. So this graphic here has been produced by the Institute for Environmental Analytics using the Living Planet Index database, work funded by DEFRA and Biodiversity Indicators Project. So just with this graphic, you can see that the colour bars show the relative changes in global temperature on the top from blue to cooler over to red for as we get to 2020. And on the bottom half, the global biodiversity from greener through to the yellow and grey, showing from the last 50 years from 1970 to 2020. So in today's webinar, we will hear about some of these consequences of climate change in our seas around the UK and the consequences for sea level rise, tidal flows and storm activity up to 2100, and what the consequences of offshore wind farm development alongside all these climate change impacts. So to start us off and introduce the topic, we're very fortunate to have Jen McNulty, who co-leads JNCC's marine management team. And she will provide us with some insights into their work and policy drivers in this space for consideration alongside the research findings from the projects. Then we'll hear from 3 of our researchers from the Accelerate project, Dr. Lucy Pacherno, Dr. Julia Rulin and Dr. Connor McCarron. And finally, I will host a short Q&A session towards the end of the webinar. So if you do have any questions as we hear the talks, if you could pop them in the Q&A tab at the bottom of your screens. And you can upvote any questions that you like using the thumbs up icons to highlight any interest in that question. And so everyone's aware this webinar is going to be recorded with the outputs to be shared in time. We will post the recording on YouTube for those that couldn't make it. So that's it for now. We hope you enjoy the webinar. I will stop sharing my screen and invite Jen McNulty. So Jen McNulty co-leads JNC's marine management team, spearheading work on Scottish and Welsh renewables, emerging climate and net zero technology and marine carbon dioxide removals. So I'll hand over to you, Jen.
Sorry, I had a problem with the mute there. Please tell me when you can see my slides.
Yep, they're up.
Grand. Thanks, Kim. It's an honour to be here to provide some scene-setting insights from across government for ECOWIN's Climate Change and the Seabed webinar. I am Jennifer McNulty, and as Kim said, I lead on Scottish and Welsh renewables alongside emerging climate technology and approaches, particularly in the offshore environment, for the Joint Nature Conservation Committee. Now, JNCC is the only statutory nature advisor to all 4 countries of the UK. We work across land and sea with partners throughout the UK overseas territories, the Crown dependencies and around the world to achieve our vision of a thriving natural environment, empowering a sustainable future. Crucially, we are responsible for nature conservation in the offshore marine environment, helping the government and industry to use the offshore environment sustainably. We do this by identifying, monitoring and advising on protected areas, by engaging in research and development, and by advising on the impacts of offshore industries. So, what are the government priorities for the marine environment? And whilst not an exhaustive list, I'm sure many of you won't be surprised to see the acceleration of offshore wind and environmental compensation in there, with multiple government consultations coming out over the last few months. Other priority marine issues are, of course, sustainable fisheries, pollution, and the ambition for clean, biologically diverse seas. And as we'll discover, nature recovery and resilience, alongside climate resilience, grows more important by the day. Indeed, one of JNCC's key priorities is to align and bolster action on the twin threats of the biodiversity and climate crisis. Fundamentally, nature degradation and climate change are 2 sides of the one coin, as brilliantly illustrated in Kim's slides at the beginning. We know climate change accelerates biodiversity loss, whilst the loss and degradation of nature releases greenhouse gases, whilst simultaneously undermining our ability to adapt to a changing climate. Indeed, globally, the truly catastrophic threat these twin crises present is that nature loss and climate change could soon cause tipping points in the natural world, leading to large, rapid, and likely irreversible changes in Earth's natural systems. Better yet, they have the potential to cascade in a domino effect, and the warmer it gets, the greater the risk. Critically, any further anthropogenic pressures which degrade environmental resilience doesn't just hinder us from adapting to climate change, it could actually allow these tipping points to trigger at lower temperatures. So there really is no route to net zero without nature recovery. But how do we meet this challenge? How do we turn science into action for people and planet? And the quick answer is it's complicated and involves balancing global, regional, domestic, and devolved policies, targets, and agreements. Now, you'll see some illustrative examples on the slides, but again, it's not an exhaustive list. And it's key to note that many of these are regularly updated or apply to specific timeframes, particularly in the domestic and devolved spheres. But let's look at a couple in tandem to see how they interact. Under the Convention of Biological Diversity, the UK needs to conserve 30% of land, waters and seas, as well as to restore 30% of degraded ecosystems. Simultaneously, the Clean Power Action Plan aims to drastically reduce fossil fuel dependency, with a promising shift to renewable energy and ambitious targets of between 43 to 50 gigawatts capacity set for offshore wind in the marine environment. But this is all against the backdrop of an accelerating climate crisis, its cumulative impacts, and a marine environment under pressure. UK seas are in poor condition, with only 4 out of the 15 indicators of good environmental status being achieved. Benthic habitats, in particular, are continuing to deteriorate. So how do we balance these nature and climate targets? How do we achieve nature recovery and net zero? And the first step is knowing what's coming. And that's why I'm delighted to pass across to Lucy, Julia and Connor, who are going to talk about the latest climate change estimates from the ECOWind ACCELERATE project and what that means for the seabed and the wider marine environment. So, over to you, Lucy.
Thanks a lot, Jen, for that introduction. Yeah, I'm delighted to be here today, and so thanks for ECOWind programme for letting us give a chance to show some of our science at this early stage in the programme. I'm gonna just share my screen. Tell me when you can see that. Okay, is it full screen?
Yep, that's all set. Thanks.
Okay, great. So I'm going to present a bit of an overview of the ECOWind ACCELERATE programme before Julia and Connor go on to talk about the more detailed results. So this is a focus on what's happening to the seabed in the context of that wider climate crisis. So we've already seen a little bit about the rapid temperature rise and that accelerated warming, how that's affecting biodiversity, but there's more climate impacts than that warming. There's a lot more going on aside. So part of ECOWind ACCELERATE is to look at how the seabed is changing in response to sea level rise and the climate crisis generating changes in storminess. So we're looking at the ecological implications of this changing seabed mobility and how that will combine with the rollout of offshore wind. There's a concern about we don't know exactly what's going to happen around the turbines, and also how those changes nearby the infrastructure will interact with the larger scale changes that are going on under climate change. So it might be changing the content of the seabed, what it's made of. Is it going to shift in class? It might change things like water clarity through changing turbidity, and then that would impact the habitats, not just of the things living in and on the seabed, but also what feeds on them. So there's an important keystone species such as sand eel really rely on the seabed fauna, and then that can cascade up to that sort of broader ecosystem. So it's everything from changing the seabed, changing those species, what feeds on them, and then cascading that up to the higher trophic levels like seabirds. So, but we'll start looking at the seabed. And we're interested to know how the placement of these offshore wind infrastructure, the rollout of large infrastructure, can affect the seabed. And that's how the hydrodynamic forces, so that's the waves, the tides, the currents, how can that control the seabed composition and thus knock on to these benthic habitats for these important species. So most of the work we're going to do is going to be predictive numerical modelling to try and make some projections into the future. So I'll present some of the model approaches, how we consider the uncertainty of climate change, and the kind of outputs that Julie's going to go on to present. So a little cartoon of what we're talking about. We're looking at what changes go on really close to the infrastructure, and then how that can sort of be put into the context of changing at the whole sort of UK continental shelf level. So we're focusing around UK seas, but the processes can be sort of applicable, and the methods are applicable to many areas, any similar shelf seas. And we're trying to quantify like what's the most important thing. So we're saying what are the important drivers, what's really moving that seabed about? Is it all down to what's happening in the wake, or is there much broader things happening? We're going to look at two main environmental drivers. That's the tidal currents and the storms. We're going to look at how the sea level rise is impacting on those tides and how the changing climate is changing that storminess. And that gives us sort of this natural variability, that baseline, what's going on today. We'll look at how that baseline natural change may be nudged in the future by man-made climate change, and then add that together with the extra layer of what's happening actually around the infrastructure, and put that all in together to talk about, well, how will these forcings change, and how could that then modify the character of the seabed itself in the future? So the model configuration we're going to use, I say we're going to use this sort of this black box on the right is the area we're looking at, which covers that whole northwest continental shelf. And a bit further out so we can get a bit of context. We'll use these hydrodynamic models. They're quite high resolution, like a 1.5. So it's like a step change. The last time this kind of thing was presented, it was about 12 kilometres. So this is a massive improvement on the kind of data sets that we used to have available for the seabed. We use the latest high resolution climate projections. So this is from the UK Climate Predictions 2018. So they're not, you might say, why are we using CMIP6? But actually the resolution is more important. So it's kind of for local projections, local climate and regional climate studies, we have to be a step behind because we need that spatial detail. And then we have a consistent set of sea level rise projections. So the regional sea level doesn't go up in a consistent way. So we've got something that matches with a real future climate change, sea level, and then we have a global wave model to look at how those global climate is also influencing this local shelf area. So we'll include the sea level rise from that. But the changing storminess is quite a nuanced piece because the way that the future waves are changing is quite complicated. overall, we're seeing actually quite a calming, a stilling in the background conditions. So when there's not a storm, actually those calm summer waves are decreasing. So in the background, that's happening. But what we're also seeing is an increase and an uptick in the frequency and intensity of the more major storms. So when we do get a storm, it can hit and they can be quite fast and quite intense. So this new infrastructure, anything, seagoing, boat work, everything will have to be thought about in this context of the day-to-day, okay, why are we worrying about this? It's calming down. But actually, when the storms hit, we have to be really resistant to that changing storminess. So that's why we need to look at these climate projections to make sure that we're getting it right in that space. And similarly, the sea level rise, that we have to use these projections to get it right around the UK. So I say we've in this study, we're going to present some future projections based on the RCP 8.5. So that's one of the CMIP 5 results. And we're taking a sort of business as usual. So this is one of the more high-end scenarios, but we've done some sensitivity tests and found that this is sort of a bounding member. So the patterns maintained are the same, they're just like the time horizon that you reach is different. So what we're saying is this is a likely future and this is a high-end future, so we can understand the direction of change and what might happen. And we're going to do it for a couple of time horizons, looking at the middle century, sort of 2050s, and round to the end century, so we can look at the acceleration of these changes and how they might impact the sea level, the storms, and therefore the seabed. There's an increasing uncertainty around all these future projections as time goes on, but this is just to say that we're using one of those higher end suggestions. The sea level rise also changes the behaviour of the oceanography on the shelf. So it changes the tidal progression. So in the future, it's not just a net sea level rise doing something flat everywhere. It changes the response of the tide. So the tide could be up to sort of 40 centimetres, 50 centimetres higher or lower in places, depending on where you are. So we make sure we factor in those changes as well. So now we're doing sea level rise plus tide plus storms and looking at how that knocks onto the seabed. So the kind of results, I'm not going to do it now, this is a bit of a spoiler for Julia's presentation, but what we're going to look at is how all those hydrodynamic forces work together to mobilise the seabed. So we do a little inverse calculation. So, okay, we say, what if we have this force on the seabed, what kind of grain size could it move? What sediment could it move? So this is kind of agnostic to what the seabed's actually made of. We're just trying to get a feel of what the force is on that. So you'll see maps like this with like a grain size. And what we're saying is under this storm, we could mobilize something that's like a pebble size, or under the calm conditions, it's sort of like fine sands and mud. So this gives kind of a physical feeling of what these hydrodynamics could really do. And then we'll use that to put into context that whole shelf-wide picture. And then we can then add back on the infrastructure so you can kind of put the two together. So what Connor's going to show is zooming into these areas. So combining that, my model on the left side with the whole continental shelf. And then he's going to zoom into the regional scale into this Irish Sea, look at some present day, that's in black, and proposed wind farm sites in pink. And then he's going to zoom down to see how these stresses change around the farm scale and all the way down to the device scale. So looking at a combination of what's happening in the wake, what's happening around the farm, and then putting it into that whole shelf context that Julia's going to talk about. And the reason we're doing all this modelling is to find out how is it really going to change the seabed. So we have this inverse calculation, what sediment could be moved by these forces, by these stresses, and what does that mean for the associated habitats? Because ongoing in the ECOWind project, in the Accelerate, there's also a piece of work about linking the habitat suitability to that seabed characteristic. So if you've got this kind of sediment, if you've got this fine sand, what likes to live there? If you've got this coarse or bare rock. So they've done some work with these drop-down cameras, both in and out of the wind farm, and they can see that they've got like nice correlations of saying what likes to live in which sediment. So that we know these physical maps can be quite predictive for the habitats that are suitable there. And you get your sort of sea urchins on the bedrock, and you get anemones that like to live in other areas. You get your little hermit crabs and the brittle stars. So though we're not actually doing an ecological model, we're sort of giving a habitat suitability prediction. And this gives an idea. There's some work going on in ECOWind ACCELERATE at Southampton with our colleagues at NOC, and they're looking at species richness. So it's sort of abundance of species, but also that biodiversity. So that's what we're trying to link back to with these physical numerical models of the physics. So I'm going to pass on next to Julia. So she's going to show you some more of these nice maps, talk about the drivers, the processes that are going on, maybe do some definitions as well, because I've probably reused these stress terms. So she'll give you the hydrodynamics behind it and show some more maps. I'll finish there. Thank you.
Thank you, Lucy. So we'll now hear from Julia Rulin, if she can just upload her slides for us. She's a researcher at the National Oceanographer Centre, sort of specialising on the understanding impacts of climate change at sea level rise. There we go, got your slides.
Can you see them full screen as well?
Yeah.
Okay. Oh, sorry. Sorry about that. It's not a real live event without this kind of issues. Right, so thank you very much, Lucy, for the introduction. Yes, and thanks for having us here to speak. As Lucy said, the first part of our project consists in looking at the modeling at a shelf scale, so everything that happens over the Northwestern European shelf at about 1.5 kilometer resolution, which for this kind of scale is quite a high resolution. And what we want to look at is the effect of sea level rise and climate change over the seabed stresses and over the transport capacity at the seabed. When I'm talking about sea level rise, what we mean is a constant, steady increase in the background sea level, which is a consequence of climate change, but is not the full signal of climate change. So we are trying to isolate that signal of rising sea level. We then also want to look at a fully forced climate change, the difference here being that in this case, we are considering changes to the atmosphere, changes to the wind, and in that case, we can see the impact of storms over our system. So when we are doing this work, we are splitting into two different types of experiment to try and isolate the sea level rise and then look at the effects of sea level rise and climate change together over the seabed stresses. Before I move on, I wanted to give you a few definitions of some of the main concepts that we'll be mentioning throughout both mine and Connor presentation. First of all, when we are talking about seabed stresses, there are two main components forming the seabed stress. When we are doing this work, we run two types of model, one wave model and one ocean model, because one component of the seabed stress comes from the wave and is derived from the orbital velocity, so that's circular motion of water particles under that occurs under waves when they are passing. And this is the way in which the wave energy gets transferred all the way down to the bottom of the sea, and it will lead to currents at the seafloor, which will induce stress over the seabed. Then from the ocean model, we take the currents that are derived by the tides and triggered by density difference and those wider scale currents, which also induce a stress at the seabed, and we combine them together offline to get a complete picture. One last thing I want to mention is that when we are talking about shallow water here, we are talking about all that happens before wave transformation, because when water gets too shallow, the seabed start interacting with those orbital velocities I mentioned before. It ends up distorting the wave, they end up breaking, and we end up having to deal with a number of processes that we don't want to resolve in this case. So why do we care about all this? We care because both wave and ocean currents are a lot of processes related to waves, ocean currents, and their interactions are directly related to the water depth. So we want to understand what would happen in the future if the sea level was to rise. Now I want to jump straight into the results. What we get from our model to investigate this type of process is this type of map. What you're looking at here is the stress at the seabed for some snapshot simulation in present day and in 2100, just to give you an overview of the type of results I'll be presenting. And the main take-home message in that study is that if you look at the differences between the two top maps, so the present day, and the two future maps, so the bottom maps, there is no big difference at a glance, right? But you can very clearly see a big difference between the two means, the left plots, and the two maximums on the right. The key concept being that overall we saw a reduction in energy reaching the seabed between the present day and the projection, but actually the difference between the quiet condition and stormy condition is really big and is what will make the biggest difference over the seabed. Now I'm going to split these processes up into smaller parts so that it's a bit clearer. If we try to isolate the effects of sea level rise and we look at what happens when rising the sea level, we see an overall reduction in the seabed stress that I mentioned before. So what you can see here are the mean and maximum over the shelf. There is an overall reduction that is steady and predictable, but quite small compared to the effects of a storm. You can see all the area where the shelf looks blue is reducing of 0.1, 0.2 Newton meters square over the means and up to 1 over the maximums. There are some area near the coast where you can see an increase in the stresses. This is because as there is an overall reduction of the seabed stress and there is a decoupling in the effect of the wave reaching the seabed, there is also less dissipation of the wave energy. So the waves reach the coast with all this extra energy that needs to go somewhere. And in those very localized coastal areas, we can see an increase in the seabed stress. Overall, though, there is a steady reduction. Then if you take that and you look at the effect of the full forcing and the full climate change, so including the effects of storm, you can see increases of up to 10 Newton per meter square in present day. So that would be the top picture on the right. And for the end century winter, we get up to 15 Newton per meter square, which is something that can move very coarse gravel. Just not that the color bar is saturated there, so it's easier to see the changes over the means. But the point is that during our winter period, the differences between a quiet summer period and a winter period is huge and much bigger than the difference between our present day condition and the future condition. So yes, we have a steady, predictable decrease in the stress that reaches the seabed, but then when a storm comes in, it can completely override that signal and really have a much stronger effect on the seabed, up to 1 order of magnitude higher compared to the mean stresses. One thing I really want to point out here is that this is not, it's not a statistical projection of what will happen in the future. We are working with very short snapshot simulation. So what this shows is a case scenario of the RCP 8.5 projection. So what it shows you is the scale of what we can expect in that case, and it's a possible future, but it's not it's not a statistical representation of what will happen in the future. Now, these effects are not the same all over the coast. There will be areas where the wave effects will matter more. There will be areas where the tides will matter more, And depending on which is the dominant driver of the signal, you might be able to act accordingly and decide what is more important for the area you live in and for that specific region. So we have tried to split the continental shelf into different areas. And as you can see, everything that is exposed to the Atlantic is really dominated by the wave signal, where big waves coming in are quite important, whereas areas where the tides are strong, like the English Channel, part of the Irish Sea, have strong components of the stress coming from the tides. Now, what does this mean in terms of sediment mobilization? Can this move the sediments? As Lucy mentioned before, what we are looking at here, it's not what is at the seabed exactly, but what we were, because our model is too coarse to look at this type of things, this will fit in better into Connor's work, but what we were able to look at is what is the biggest grain size that the flow can move, so the transport capacity in the model. Now, the way to read this map, to guide you through it, what you see here over the x-axis, you have the area of shelf that is moved. If you go up over the y-axis, what you see is the grain size, so from very fine to coarser grain size. So what you see in this plot, when you move towards the northwestern region of the plot, if you want, is that bigger areas of coarser sediments are moved. So what this shows is that during quiet summer times, not a lot less sediment is moved. And then you get to stormy winter times, and we see a huge increase in the area of shelf that can be mobilized. If you want to focus, for example, on the very coarse sand, just to help understand the plot, if you follow along that green line for the very coarse sand example, you can see that during the summer times, where those blue lines are crossing over, you have about 500,000 kilometers square of course, very coarse sand that can be moved. Whereas if you look at where the red line is, there is about 1 million kilometers square of very coarse sand that can be shifted. Another way to look at this transverse capacity is through maps, as Lucy showed briefly before. And in this case, we are trying to focus on which area we expect to move more in this specific scenario. Well, what you see on the left there is the transport capacity for a present day winter, so a stormy period as well. And on the right, the transport capacity for a future winter. And as you can see, in future, when we expect storms to become more frequent and more intense, you end up with much bigger areas of the shelf where coarser sediment is mobilized. Now, whether this matters or not will depend on what is actually there on the seafloor, but there are areas like, for example, just to give an example, the Dogger Banks here in the middle of the North Sea, where we know there is very fine sand today. And you can see in this projection, much coarser sediments can be mobilized. So this, that we may well see an effect in some of the areas of the shelf. Yes, so overall, what we've seen looking at the shelf scale is that tides and seabed stresses, tides today can cause seabed stresses of up to 8 Newton per meter square. Storms today can reach up to 10 Newton meter square. These are types of stresses that can move things like medium gravel. The sea level rise is expected to reduce and decouple the signal between the waves and the seabed, so reduce the seabed stresses overall of about 1 Newton per meter square, which is something that can move very coarse sand. And this is a steady, predictable background signal, but that is quite small compared to the effect that we expect from future storm, which can come in and move things like very coarse gravel with up to 1 order of magnitude higher stresses. And hopefully this type of maps can help gaining a better understanding of what we can expect in future. This is all I wanted to say. I will stop sharing now. I think what I've shown here is the shelf scale work without infrastructure. And the next step then is to look at how this fits in with, how this natural variability fits in with offshore wind farm infrastructure, which is what Connor is going to talk about. Thank you.
Thank you,
Thanks,
Julia. So we're now going to hear from Dr. Connor McCarran. I'll give you a second to upload your slides.
There we go.
So Connor is a senior scientist in Coast and Oceans Group at HR Wallingford. And that is all set. Thanks, Connor.
Thanks, Kim. And thanks for the segue, Julia, to the work looking at the Eastern Irish Sea. So we've heard about the effects that sea level rise and change in storminess might have on bed shear stresses as a proxy for seabed mobility in the future. And this part of the work is really looking at how then will the presence of offshore wind farm infrastructure combine with sea level rise and change in storminess to further affect that seabed mobility. So the study area that we're working in is the Eastern Irish Sea or Liverpool Bay, and it's an area of rapid offshore wind farm expansion. So at the minute, there's 9 existing offshore wind farms with about 2.9 gigawatts of capacity, and there are 4 round 4 proposed offshore wind farms, which is going to significantly increase that capacity in the future. The reason why we've chosen the Eastern Irish Sea is it's a data-rich environment. So there's been extensive research that's been conducted there in the past. But at the same time, because of the development there, there's also access to, for example, pre and post-construction surveys and the associated data through arenas like the Marine Data Exchange. And it's also an area where we have collected additional data as part of the ECOWind ACCELERATE project, which is quite helpful due to the proximity of Bangor University to the Eastern Irish Sea and access to the research vessel. So I'm just going to touch on, oh, sorry, my screen wasn't changing. I'm just going to touch on the additional data that's been collected, and this is just an example of one of the areas where some data has been collected. So this monopile here, this is monopile 8 of the Rill Flats offshore wind farm. And around this monopile, we got access to deploy 4 bottom-mounted ADCPs, which you can see in the red dots in this figure. The monopile is actually located here. So we've got 3 ADCPs in the flood wake and 1 ADCP in the ebb wake. And then we also collected some extra multibeam and backscatter data around the monopile, as well as sediment samples. And you can see this backscatter underlying the map here. So in this backscatter image, brighter values are indicative of coarser sediment, and darker sections of the image are indicative of finer sediment. And what we can see is in the flood wake of this monopile, we have a coarsening of the seabed sediment approximately 200 meters downstream from the monopile. And I'm going to come back to this data later on in the presentation. So as Lucy and Julia mentioned, the UK shelf scale modelling was conducted at 1.5 kilometers, but at this resolution, it's maybe not resolved enough to be able to include the offshore wind farm infrastructure in the model. So what we're doing in this modelling is we're taking Lucy and Julia's boundary conditions from the UK shelf scale model, so their waves and tidal levels, and we're using them to force the boundaries of a much higher resolution telemac model, which has spatially varying resolution. And you can see this spatially varying resolution if we zoom into, for example, the North Hoyle offshore wind farm, and then into an individual monopile. So in our model, we've got all of the existing and all of the proposed monopile foundations and associated substations included in the model as islands. Okay, so the first question in kind of disentangling the effects of climate change, sea level rise, storminess, and the offshore wind farm infrastructure is first to look at what effect the offshore wind farm infrastructure has on bed shear stress. And in this plot, what you're seeing is the change in peak bed shear stress between the present day, where there are existing offshore wind farms and monopiles, versus a past scenario where there were no monopiles included in the mesh. And the effects that you can see vary across different scales. So at this scale, generally what we see is changes outside of the wind farm footprints are in the order of plus or minus 0.1 Newton per meter squared. And then within the actual offshore wind farm footprints themselves, we get reductions in bed shear stress by up to 0.5 Newton per meter squared. But then if we zoom right down into the actual devices themselves, what we see is very localized in the flood wake of the monopile. We get an enhancement of the bed shear stress by up to 6 newtons per meter squared. And to put this in context, 6 newtons per meter squared is probably enough bed shear stress to move a grain size around about the size of 5p piece. So what we're seeing is a localized increase in bed shear stress directly in the wake of the monopiles, and then a reduction in bed shear stress further downstream. Coming back to the data that was collected at Rill Flats, the reason why that's useful is in these types of models for calculating the bed shear stress, the most common approach is using the quadratic stress method. And in applying this method, what we see is we don't get any reduction of the we get a reduction of the bed shear stress in the wake of the monopile, and we don't see any scour coming out from those results. So as part of the ACCELERATE project, we're using a different approach. So we're using a blended turbulent kinetic energy method. And essentially what that does is where there are structures that are generating turbulent kinetic energy, we calculate the bed shear stress based on that TKE that's coming off the structure. But away from the structures where the TKE is significantly reduced, then we revert to using the quadratic stress method. And this is something that, as part of the ACCELERATE project, we've validated this approach against a series of flume experiments that were conducted at HR Wallingford, and also against the field observations that were collected. And one of the outputs of the work at the minute is validation of the blended TKE method, which our colleague Chris has been leading on, and hopefully we'll get that paper published soon. It's currently under review with Nature Comms. Okay, so that previously I talked about the existing offshore wind farm infrastructure, and then if we look at existing and the proposed offshore wind farm infrastructure, we see a similar picture. So again, we get a reduction of the bed shear stress generally within the footprint of the wind farms, but we get this wake enhancement directly in the wake of the monopile. And one of the interesting things that we can see from these results is as we go from the existing kind of round 3 size offshore wind farm monopiles to the round 4 and deeper water, the reduction of the bed shear stress is less condensed in the offshore wind farm footprint, and we also get a bit of bed shear acceleration between the strings of the proposed monopiles. Okay, so that's the effect of offshore wind farm infrastructure. How do these combine now with sea level rise and change in storminess? So we get similar results to what Lucy and Julia's model showed for the UK continental shelf. So in terms of sea level rise, we get a general reduction in the mean bed shear stress associated with sea level rise decoupling that bed shear stress from the bed. In terms of future storms, what we're seeing is we're getting an increase in the bed shear stress on westward facing coasts and shallow areas. And then combining sea level rise and future storms together, we get a bit of a mixed picture. So in deep water, beyond the wave base, sea level rise effects dominate, and you can see this by the reduction in bed shear stress in the deeper water areas. Whereas in shallow areas where inshore of the wave base, the storm wave effects dominate. So then how does this combine with the offshore wind farm infrastructure? This is an example now, but with the monopiles present in the mesh. And what we can see is where the sea level rise signal dominates, the large scale reduction of bed shear stress associated with the monopiles contributes to the reduction in bed shear stress associated with sea level rise. Whereas in areas where the storminess signal dominates, the reduction of bed shear stress associated with the offshore wind farms counteracts the increased bed shear stress associated with storminess. But in all of the cases, or both of these cases, the TKE generated bed shear stress in the immediate wake of the monopiles dominates both the sea level rise and storminess signals. Okay, so some quick conclusions then, just to recap. So with offshore wind farm infrastructure, we get a reduction in the bed shear stress across the footprint of the wind farms and a localized increase in bed shear stress directly in the wake of the monopiles. Sea level rise decouples the bed shear stress from the bed and generally reduces the bed shear stress. Storminess increases it on westward facing coasts and shallow waters. With combined sea level rise and storminess, we get storminess dominating in shallow areas and sea level rise dominating in deeper waters. And then with offshore wind farm infrastructure, they contribute to the reduced bed shear stress where sea level rise dominates, and they counteract the increased bed shear stress where storminess dominates. But the localized wake enhanced bed shear stress dominates both the sea level rise and the storminess signal. And that's all from me.
Thank you, Connor.
Thanks,
so
Kim.
we're now going to head into our Q&A session. So if I could just invite all our speakers today to just come back on camera and unmute. Everyone, please feel free to drop a question in the Q&A chat. I believe you can raise your hand and we can allow you to unmute your mic if you have a question that you want to ask. So I think we have a question for Julia. So you presented sediment distribution for 1996 alongside a conceptual projection for 2090 based on increased seabed energy. Have you compared your model outputs with more recent sediment maps to assess whether any of the inferred changes are already visible and to help validate potential sediment mobilization?
Hi. Yes, so thank you for the question. The answer is yes. For our present day simulation, we have compared when we have estimated the sediment that can be moved by the seabed stresses to make sure that it matches what we know about the present day condition. We have validated it against Wilson's maps that is a work that look at sediment that is actually there at about 10-kilometer resolution, which is the best that we've got available today. And it looks like our work does match the maps, the sediments map that we had. It is a much better resolution that we're showing though. And so yes, we have validated against the present day condition, but it's the what is on the seafloor is something that changes quite fast and can move quite quickly, and we don't know exactly what is everywhere at the resolution that we show in the model. So we've done the best that we can with the with what was available. Yes.
Can I add to that? Because we've also it's kind of goes back to the observations and what's available. So we talked to the guys at CSAS who are working on the One Benthic project, and that's been really helpful because they've got some there's a nice database of existing sediment types. So So there's that database as well as the Wilson data set. And what you'd really like to see is sort of before and after one of these storms, to actually see how that character is changing as they come through, because you might get, depending on when you've taken that sediment sample or had a look at the seabed, it might have been like super calm for ages, and then you get one of these large events that comes through. So because these storm disturbances are, like, say, transient and like so impactful, that's kind of dependent on that as well. The seabed's like really, yeah, it's very mixed in some places, especially in the Irish Sea, which is why we've used that as that test case, because it's got all those different habitats in one place.
Thanks. And just to add to that, both Julia and Lucy, this is probably a question for you. Could you touch on a bit more around the uncertainty when we're dealing with climate projections, and the issues around projections for one storm and maybe the differences in resolution?
Yes, maybe I can start, and Lucy, you can add if you want. But one thing I really wanted to be clear in this work is that what we're looking at is a case scenario of a projection. When we're looking at sea level rise, there are different ways in which this steady rise in the sea level can shift, and we are focusing on the RCP 8.5 projection. That is one very specific projection, and it's quite a high-end, quite an extreme scenario. So it's what we are showing is not a statistics of what will definitely be there in the future, but it's a snapshot of a possible future, which shouldn't be underestimated or discounted. And it can happen, but it's just not the full picture. And a lot more work should be done to understand, maybe have a better understanding of what the uncertainties are in these projections that we're showing. It is still extremely useful to get this range and understand how big the effect of this extreme storm can be in future. I think it gives a good understanding of what an extreme can do to our seabed. I don't know if Lucy, you want to add anything on
Yeah,
that?
well, and there's another question in the chat that kind of follows up on that from Mikhail, who's asking about the future change in the extremes. So yeah, certainly, as Julia says, this is just one storm. That's because the storminess is absolutely the most uncertain thing we've got in the future. So we're just showing the impact of one storm, but really you want to know what's going to happen in terms of the wave height and the wave period and the wave direction, because that's going to be really important for the exposure of different coasts depending on where those storms are hitting. Also, as Julia mentioned, that combination with the sea level rise and the waves. So she showed this effect where, because the wave energy isn't being dissipated by that shallow water, that little bit of deepening is actually increasing the coastal exposure for those areas. So there's quite like a complicated system going on. And yeah, so the uncertainty in the wave, in the storms, is the thing that knocks onto the uncertainty from those wave conditions. But that's the largest error bar. So what Julia showed was that, like, calm to storm is that order 10 Newton per meter squared. And that's the one that we're most uncertain about, but it is the thing that's most impactful at the bed. So what we're doing in this is looking at the RCP 8.5 because it's the most intense climate feature, and we've gone and picked the most intense storm over that 50-year, mid-century 2050s and end-century 2090s. And looking at that sensitivity, we're just saying, in that future climate, that sort of error bar is sort of 0.5 Newton per meter squared. But you put that in the context of like storm versus no storm, that's like 10 Newton per meter squared. So what we're trying to do is reduce or quantify that uncertainty in the future projections.
Thanks, Lucy. I think we've got one more question from Matt. How well does the local RC Telemac model validate against the long-term metocean measurement data, particularly currents, that have been collected for all of the existing and proposed offshore wind farm projects?
Thanks, Kim. Thanks for your question, Matt. And I was just typing in the chat there. So we took our present day model and validated against measurements that we had in terms of water levels, current velocities, and also waves from some of the different observation locations across the Eastern Irish Sea. I don't know if it's helpful, but I can share a slide and show what those results look like if it helps Matt picture it. So I just share my screen. So this is an example of the levels on the left. So we've done some comparisons, just spreading our observations around the coastline from Heysham round to Llandudno. And we're doing, I think, quite a good job in terms of not just levels, but also the currents, observed currents at one of the observation locations. So this was a BODC location where they measured currents. And you can see the predicted current speeds versus observed in the bottom plot, and the directions in the bottom right plot. And then this is the validation against waves for a particular storm as well too, and the models capturing the peak wave heights well and the wave directions pretty well.
Thanks, Connor. And just a sort of open question, how large are all of these climate changes in the context of other environmental drivers?
I guess, yeah, because what we've been talking about today is those sort of physical impacts on the seabed from the waves and the storms and the tidal currents. But these are only one environmental driver. So there's also this rapid warming that's going on at the same time. There's other work going on in the other ECOWind partner projects. For example, Pelagio's looking at how the water column changes and how like extra mixing around turbines might change things. So this is kind of just one piece of the puzzle for sure, that we've got to say what happens at the seabed, what happens in the water column, what happens in the atmosphere, and then get all those cumulative effects of the environment combined with the cumulative effects of having the infrastructure in there. And I think the rapid warming is one to really flag up, although it wasn't the focus of this webinar, because it's particularly dangerous on the shelf. So we get a lot of surface warming. It might increase stratification offshore in deeper water, but in the shelf seas and shallow waters, that heating can go right down to the seabed. So that's going to be really impactful for the benthic species and stuff living on the seabed. So it can also lead to the changing position of front, and that impacts on where the fish are, seabed feeding areas. So there's a lot of compounding effects. So this is, yeah, I realise this is only one piece of the picture.
Thanks, Lucy. Another question for Connor. Assuming storms can extend the depth at which wave action can affect the seabed and the possibility of increasing storminess in the future, might seabed shear effects also be seen around anchor systems for future floating turbines, or are they expected to be too deep?
That's a good question. I'm not too familiar with floating systems or the types of water depths that they're located in, but I suppose it depends on the size of the incident wave height, whether that wave base will touch the seabed and the depths that they're located in, and then you'll get not just trying to consider what effect the wave base will have. You'll have the wave base on top of then potentially the sea level rise. So it's a bit of a tricky question. I'm not sure of the water depths associated. Sorry.
I think our programs EcoFlow, which are only just kicking off now, are definitely more looking at that physical processes around the impacts of floating offshore wind. So there'll be more results to come from EcoFlow on that. I'll come to you, Jen. After hearing these results today, how do you think this work on climate change might be able to inform your work at the JNCC?
Oh, could help in quite a few ways. First of all, as you know, Lucy and others talked about, we are looking at a very busy picture. There's a lot of cumulative impacts. And what's great about this project is that we're starting to see several of these cumulative impacts be brought together. We obviously advise on benthic habitats, so the more information we have, the better informed we can be. And I think being able to look at the future sea state and things like that as well is very valuable for, you know, the work that kind of supports that advice. So, you know, are our research vehicles or the innovative monitoring technology we're talking about, could this handle, you know, these future storms? So that it's this whole picture, but having these projections or these estimates are very valuable. And yeah, the more we can find out about these cumulative impacts, particularly around the offshore wind structures, the better it can help us when we talk about, you know, co-location of different industries, you know, marine protected areas, things like that. It can help us with our conservation advice and to better understand the environmental impacts.
Lovely, thanks, Jen. And I'm just going to pop on my last slide, but if any of the other panel, do you have any final reflections? No? Okay, well, we'll wrap it up there. Thank you very much for everyone for attending. We do have some more webinars coming in 2026 next year. So those webinars will be the impacts of offshore wind developments on seabed prey availability and foraging behaviour. There'll be one coming on the impacts of offshore wind on marine physical processes. And with all our projects producing really valuable tools, there will be a webinar on decision support tools to support ecosystem scale offshore wind management. We do have a short form. If you follow this QR code that's up on the slide here, this will just take 2 minutes for you to fill in and provide us with some feedback on today's webinar so we can make the next round even better. Lovely. Okay, I'll end it there. Thank you very much to all our speakers and thank you for attending. Thanks. Bye.